NCERT video welcomes you. Today we are going to start Chapter 5 Prime Time. Let's start Chapter 5 Prime Time. 5.1 Common Multiples and Common Factors. Idli Vada Game. Children sit in a circle and play a game of numbers. One of the children starts by saying 1, the second player says 2, and so on. But when it is the turn of 3, 6, 9, and so on, multiples of 3, the player should say idli instead of the number. When it is the turn of 5, 10, and so on, that is multiples of 5, the player should say vada instead of the number. When a number is both a multiple of 3 and a multiple of 5, the player should say idli vada. If a player makes any mistake, they are out. The game continues in rounds till only one person remains. For which numbers should the players say idli instead of saying the number? These would be 3, 6, 9, 12, 18, and so on. For which numbers should the players say vada? These would be 5, 10, 20, and so on. Which is the first number for which the players should say idli vada? It is 15, which is a multiple of 3 and also a multiple of 5. Find out other such numbers that are multiples of both 3 and 5. These numbers are called common multiples. Figure it out. 1. At what number is idli vada said for the 10th time? For the first time on 15th, for the second time on 30, third time on 45, similarly on 10th time, that is 15 multiplied to 10. If you have observed, this is 15 into 1, this is 15 multiplied to 2, this is 15 multiplied to 3. Similarly, the 10th one will be 15 multiplied to 10, that is 150. The answer is 150. 2. If the game is played for the numbers from 1 till 90, find out A. How many times would the children say idli, including the times they say idli vada. For this, you have to count how many times the multiple of 3 occurs. That is 3, 6, 9, 12, like that, up to 87 and 90. If you count that, you will get 90 divided by 3, that is 30 times. For simplicity, if you have counted the number of multiples of 3 between 3 and 30, that is 3, 6, 9, 12, 15, 18, 21, 24, 27, and 30. How many times? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That means from 3 to 30, the number of multiples of 3 is 30 divided by 3, that is 10. Similarly, from 1 to 90, there will be 90 divided by 3 or 30 such numbers, at which children will say idli. B. How many times should the children say vada, including the times they say idli vada? 5, 10, 15. Similarly, 85 and 90. The answer will be 90 divided by 5, that is 18 times. C. How many times would the children say idli vada? That is multiples of 15. That is 90 divided by 15 or 6. You can count 15, 30, 45, 60, 75 and 90. 1, 2, 3, 4, 5, 6. 3. What if the game was played till 900? How would your answers change? Since 90 is replaced by 900, that is 10 times, so answers will become 10 times. The first answer will become 900 divided by 3, that is 300 instead of 30. The second one, 900 divided by 5, that is 180 instead of 18. And the third one, 900 divided by 15. The answer will be 60 instead of 6. 4. Is this figure somehow related to the idli vada game? And imagine playing the game till 30. Draw the figure if the game is played till 60. Figure 5.1. In the middle, you can see common multiples of 3 and 5. In the first circle, you can see multiples of 3 such as 3, 9, 12, 21, 18, 27 and so on. In the second circle, you can see 5, 10, 25, 20 that are multiples of 5, and in the middle you can see common multiples of 3 and 5. Let us now play the idli vada game with different pairs of numbers A, 2 and 5. That is, idli will be said when it will be 2, 4, 6, 8, 10, 12 and so on. Vada will be said when there is 5, 10, 15, 20, 25 and so on. And idli vada will be said when there is multiple of 2 and 5, that is 10, 20, 30, 40 and so on. So in the first list 10 and in the second list 10, 20 and the numbers that are in the third list, that is in the idli vada, should be crossed out. That is, idli will be said only for numbers 2, 4, 6, 8, 12, 14, 18, then 22, then 28, then 32, like that. Vada will be said for 5, 15, 25, 35, 45 and so on. And idli vada will be said when there is multiple of 10. 10, 20, 30, 40 and so on. B. 3 and 7. Similarly, you can do for 3 and 7. C. 4 and 6. You can do that. We will say idli for multiples of the smaller number, vada for multiples of the larger number, and idli vada for common multiples. Draw a figure similar to figure 5.1 if the game is played up to 60. This boy says, yesterday we played this game with two numbers. We ended up saying just idli or idli vada and nobody said just vada. One of the numbers was 4. Oh, what could be those numbers be? If this happens that from the two numbers selected, one is multiple of other or the other is factor of the first one, that only idli or idli vada will be said, not just vada. For example, if one number is 2, other is multiple of it, such as 4. Here 4 has been taken, so I am taking 4. Then this happens that common multiples, that is 4, 8, 12, 16, like that. When it comes, idli vada will be said. And for the multiples of 2 that are not in the list of common multiples, such as 2, 6, 10, 14, 18, 22, like that, idli will be said. Since multiples of 4 are already there in the common multiples, so there happens that nobody gets chance to say vada. Which of the following could be the other number? We have already taken 2 on the previous page. Let's take the number 8, that is multiple of 4. If one number is 4 and other is 8, then common multiple, that is 8, 16, 24, 32, 40, like that. When they comes, idli vada will be said, and idli will be said on the multiples of 4 which are not in the list of common multiples. That is 4, 12, 20, 28, 36 and so on. Vada is never said as multiple of 8 are already there in the list of common multiple. So the number could be 2 or 8 that are either factor of 4 or multiple of 4. Jump jackpot. Jumpy and Grumpy play a game. Grumpy places a treasure on some number. For example, he may place it on 24. Jumpy chooses a jump size. If he chooses 4, then he has to jump only on multiples of 4 starting at 0. Jumpy gets the treasure if he lands on the number where Grumpy placed it. Which jump sizes will get Jumpy to land on 24? If he chooses 4, Jumpy lands on 4, 8, 12, 16, 20, 24, 28, and so on. Other successful jump sizes are 2, 3, 6, 8, and 12. You can see on this number line. Jump size 2 will take you to 24. Jump size 3 will take jumpy on 24. Similarly, jump size 4, jump size 6, jump size 8, jump size 12 will take jumpy on number 24. What about jump sizes 1 and 24? Yes, they also will land on 24. You can see here. Jump sizes 1 will cover every number, and the requirement is to reach on 24. So jump size of 24 will do that. The numbers 1, 2, 3, 4, 6, 8, 12, 24 all divide 24 exactly. Recall that such numbers are called factors or divisors of 24. Grumpy increases the level of the game. Two treasures are kept on two different numbers. Jumpy has to choose a jump size and stick to it. Jumpy gets the treasure only if he lands on both the numbers with the chosen jump size. As before, Jumpy starts at 0. Grumpy has kept the treasure on 14 and 36. Jumpy chooses a jump size of 7. Will Jumpy land on both the treasures? Starting from 0, he jumps to 7, 14, 21, 28, 35, 42, and so on. We see that he landed on 14 but did not land on 36. So he does not get the treasure. What jump size should he have chosen? The factors of 14 are 1, 2, 7, 14. So these jump sizes will land on 14. The factors of 36 are 1, 2, 3, 4, 6, 9, 12, 18, and 36 itself. These jump sizes will land on 36. So the jump sizes of 1 or 2 will land on both 14 and 36. Notice that 1 and 2 are the common factors of 14 and 36. The jump sizes using which both the treasures can be reached are the common factors of the two numbers where the treasures are placed. What jump size can reach both 15 and 30? There are multiple jump sizes possible. Try to find them all. Factors of 15, factors of 30, so the common factors are 1, 3, 5, and 15. Jump sizes of these common factors will enable to reach the two treasures kept on 15 and 30. Look at the table below. What do you notice? You can see some numbers are encircled and some are colored. Let's see the colored numbers, that is 33, 36, 39, 42, 45 and so on. That is the multiples of 3. And the encircled numbers, that is 32, 36, 40, 44, that is the multiples of 4. Few numbers such as 36, 48 are common factors of 3 and 4. Since the first one is multiple of 3, second one is multiple of 4, common factors will be 36, 48, 60 and the next one, that is 72 and so on. In the table 1, is there anything common among the shaded numbers? Yes, they are multiple of 3. 2. Is there anything common among the circled numbers? Yes, they are multiple of 4. 3. Which numbers are both shaded and circled? What are these numbers called? Numbers that are shaded as well as encircled are 36, 48 and 60. These numbers are called common multiples. Figure it out. 1. Find all multiples of 40 that lie between 310 and 410. Since 40 has 0 at its units place and 4 at tens place, the multiples of 40 will be similar to that of 4. Like this. They will have a additional 0 at its units place. Like this. So, since the questions ask multiples of 40 between 310 and 410, the answer will be 320, 360 and 400. 2. Who am I? A. I am a number less than 40. One of my factor is 7. The sum of my digits is 8. Since the number has 7 as the factor, so we can write all multiples of 7 and check for which the sum of digits is 8. Kindly note that you have to write numbers less than 40. If you observe this carefully, you can see 35 has 5 at its units place and 3 at its tens place, and sum of the digit is 8. So the answer is 35. B. I am a number less than 100. Two of my factors are 3 and 5. One of my digits is one more than the other. Since factors are 3 and 5, so the number could be multiple of 15. That is 15, 30, 45, 60, 75, 90. It is said that the number is less than 100 and its digits are one more than the other. So the answer is 45. 3. A number for which the sum of all its factors is equal to twice the number is called a perfect number. The number 28 is a perfect number. Its factors are 1, 2, 4, 7, 14, and 28. Their sum is 56, which is twice 28. Find a perfect number between 1 and 10. The answer is 6. Its factors are 1, 2, 3, and 6 itself. If you add its factors, you will get 12. That is double of 6. So 6 is a perfect number. 4. Find the common factors of a, 20 and 28. Factors of 20, factors of 28, common factors are 1, 2, and 4. B. 35 and 50. Factors of 35, factors of 50, common factors 1 and 5. The answer is 1 and 5. Similarly, you can find C, 4, 8, and 12, D, 5, 15, and 25. 5. Find any three numbers that are multiples of 25 but not multiples of 50. First, write the multiples of 25. Then cross out multiples of 50. You can write any number from all these four numbers. The answers could be 25, 75, 125, 175, then 225, 275, and so on. You have to write only three numbers from these numbers. 6. Ansu and his friends play the Idli Vada game with two numbers, which are both smaller than 10. The first time anybody says Idli Vada is after the number 50. What could be the two numbers be, which are assigned Idli and Vada? The answer could be 7 and 8, 7 and 9, 8 and 9. That is any two number whose multiples is greater than 50, and those two numbers have no common factors except 1. You can see no common factor between these pair of numbers, and their product is more than 50. Kindly check that. 7. In the treasure hunting game, Grumpy has kept treasures on 28 and 70. What jump sizes will land on both the numbers? Let's check it out. Factors of 28: 1, 2, 4, 7, 14, 28. Factors of 70: 1, 2, 5, 7, 10, 14, 35, and 70 itself. Common factors: 1, 2, 7, 14. If 1, 2, 7 or 14 chosen as jump sizes, then it is certain that treasures kept at 28 and 70 will be plundered. 8. In the diagram below, Guna has erased all the numbers except the common multiples. Find out what those numbers could be and fill in the missing numbers in the empty regions. You can see it is written common multiples 24, 48, 72 in the middle. That means you have to choose two numbers such that their multiples has 24, 48 and 72. You can find factors of 24, 48 and 72 and guess those numbers. For example, if you find factors of 24, that is 1, 2, 3, 4, 6, 8, 12, 24. Factors of 48, 1, 2, 3, 4, 6, 8, 12, 16, 24 and 48. Factors of 72, 1, 2, 3, 4, 6, 8, 9, 12, 16, 18, 24, 36 and 72. For example, you can take any number from the factors of 24 for the first circle. For example, I am taking 8. And for the second circle, you can take any number that is not factor of 24 but present in the factor of 48 or 72. For example, you may take 16, 9, 18, 36, 48, 72, etc. For simplicity, I am taking 9. Then you can write here 8, 16, 24 is already there, 32, then 40, 48 is already there, 56, 64, 72 is already there, 80, and so on. You can write multiples of 9 in the second circle: 9, 18, 27, 36, 45, 54, 63, 72 is already there, 81, and 90, and so on. 9. Find the smallest number that is a multiple of all the numbers from 1 to 10 except 7. The answer is 360. 10. Find the smallest number that is a multiple of all the numbers from 1 to 10. The answer is 2520. That is 7 times 360. 5.2 Prime Numbers. Guna and Ansu want to pack figs, anjeer, that grow in their farm. Guna wants to put 12 figs in each box and Ansu wants to put 7 figs in each box. How many arrangements are possible? Think and find out the different ways how 1. Guna can arrange 12 figs in a rectangular manner. 2. Ansu can arrange 7 figs in a rectangular manner. Guna has listed out these possibilities. Observe the number of rows and columns in each of the arrangements. How are they related to 12? You can see a column having 12 blank spaces. 6, 7, 8, 9, 10, 11, 12. Similarly, you can see two columns with 6 spaces in each column. 1, 2, 3, 4, 5, 6. Similarly, you can see a rectangular arrangement having 3 columns and 4 rows. 1, 2, 3, 3 column, 1, 2, 3, 4. In the first arrangement, there is 12 into 1, that is 12 spaces. In the second arrangement, there is 6 into 2, that is 12 spaces. In the third arrangement, there is 4 into 3, 12 spaces. So, Guna can arrange 12 figs in these rectangular manners. Similarly, Ansu can arrange 7 figs in rectangular manner in only one way, like this. In the second arrangement, for example, 12 figs are arranged in two columns of 6 each, or 12 is equal to 2 into 6. Ansu could make only one arrangement, 7 into 1 or 1 into 7. There are no other rectangular arrangements possible. In each of Guna's arrangement, multiplying the number of rows by the number of columns gives the number 12. So, the number of rows or columns are factors of 12. We saw that the number 12 can be arranged in a rectangle in more than one way, as 12 has more than two factors. The number 7 can be arranged in only one way, as it has only two factors, 1 and 7. Numbers that have only two factors are called prime numbers or primes. Here are the first few primes: 2, 3, 5, 7, 11, 13, 17, 19, etc. Notice that the factors of a prime number are 1 and the number itself. What about numbers that have more than two factors. They are called composite numbers. The first few composite numbers are 4, 6, 8, 9, 10, 12, 14, 15, 16, 18, 20, etc. What about 1, which has only one factor? The number 1 is neither a prime nor a composite number. How many prime numbers are there from 21 to 30? How many composite numbers are there from 21 to 30? Let's check it out. 21 is a composite number, 22 is a composite number, 23 is a prime number, 24 composite number, 25 composite number, 26 composite number, 27 composite number, 28 composite number, 29 prime number, 30 composite number. 23 and 29 are prime numbers because they has only 1 and the number itself as their factors. Can we list all prime numbers from 1 to 100? Here is an interesting way to find prime numbers. Just follow the steps given below and see what happens. Step 1. Cross out 1 because it is neither prime nor composite. Step 2. Circle 2 and then cross out all multiples of 2 after that. That is 4, 6, 8 and so on. Step 3. You will find that the next uncrossed number is 3. Circle 3 and then cross out all the multiples of 3 after that. That is 6, 9, 12 and so on. Step 4. The next uncrossed number is 5. Circle 5 and then cross out all the multiples of 5 after that. That is 10, 15, 20 and so on. Step 5. Continue this process till all the numbers in the list are either circled or crossed out. Like this. All the circled numbers are prime numbers. All the crossed out numbers other than 1 are composite numbers. This method is called the sieve of Eratosthenes. This procedure can be carried on for the numbers greater than 100 also. Eratosthenes was a Greek mathematician who lived around 2200 years ago and developed this method of listing primes. This boy says, it is definitely not some magic. There should be a reason why it works. You can see primes 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89 and 97. Guna and Ansu started wondering how this simple method is able to find prime numbers. Think how this method works. Read the steps given above again and see what happens after each step is carried out. Figure it out. 1. We see that 2 is a prime and also an even number. Is there any other even prime? No. 2. Look at the list of primes till 100. What is the smallest difference between two successive primes? What is the largest difference? The smallest difference is 1, that is between 3 and 2. Largest difference is between 97 and 89, that is 8. You can see it here. 3 minus 2, that is smallest difference is 1. Largest difference is between 97 and 89, that is 97 minus 89, that is equal to 8. 3. Are there an equal number of primes occurring in every row in the table on the previous page? Which decades have the least number of primes? Which have the most number of primes? In the first row, you can see 4 primes. In the second one, you can see 4 primes. In the third one, you can see 2 primes, then 2 primes, then 3 primes, then 2 primes, then 2 primes, then 3 primes, then 2 primes, then 1 prime. That means the first 2 rows has same number of primes and the last row has minimum number of primes. Primes through the ages. Prime numbers are the building blocks of all whole numbers. Starting from the time of the Greek civilization, more than 2000 years ago, to this day, mathematicians are still struggling to uncover their secrets. Food for thought. Is there a largest prime number? Or does the list of prime numbers go on without an end? A mathematician named Euclid found the answer, and so will you in a later class. Fun fact: the largest prime number that anyone has written down is so large that it would take around 6500 pages to write it. So they could only write it on a computer. 4. Which of the following numbers are prime? 23, 51, 37, 26. The answer is 23 and 37 because they has only two factors, that is 1 and the number itself. 5. Write 3 pairs of prime numbers less than 20 whose sum is multiple of 5. The answer is 2, 3 and 5. Their sum is 10, which is multiple of 5. 6. The numbers 13 and 31 are prime numbers. Both these numbers have same digits 1 and 3. Find such pairs of prime numbers up to 100. From this list, you can see 13 and 31. Similarly, 17 and 71, 37 and 73, similarly 79 and 97. Their digits are reverts. 7. Find 7 consecutive composite numbers between 1 and 100. The answer is 90, 91, 92, 93, 94, 95, 96. That is from 90 to 96. Both are included. 8. Twin primes are pairs of primes having a difference of 2. For example, 3 and 5 are twin primes. So are 17 and 19. Find the other twin primes between 1 and 100. Twin primes here. 3 and 5, 11 and 13, 17 and 19, 29 and 31, 41 and 43, 59 and 61, 71 and 73. 9. Identify whether each statement is true or false. Explain. A. There is no prime number whose unit digit is 4. Statement is true as all numbers ending with 4 is divisible by 2. So their factors will be 1, 2 and the number itself. B. The product of primes can also be primed. False, as their factors will be more than 2. C. Prime numbers do not have any factors. False. We know prime numbers has only 2 factors. D. All even numbers are composite numbers. False, because 2 is even number as well as prime number. E. 2 is a prime and so is the next number 3. For every other prime, the next number is composite. It's true. 10. Which of the following numbers is the product of exactly 3 distinct prime numbers? 45, 60, 91, 105, 330. For example, let's take 91. 91 can be written as product of 7 and 13. But question asks product of exactly 3 prime numbers. Here is only 2. Let's take another one, that is 105. It can be written as 3 into 35, and 35 can be split into 5 into 7. You can see 3, 5 and 7. All three are prime numbers. So the answer is 105. Kindly do for the rest ones. 11. How many 3-digit prime numbers can you make using each of 2, 4 and 5 ones? The numbers you can make using 2, 4 and 5, which are of 3 digits. Since you can see unit place as either 2, 4 or 5. If 2 or 4, that means it is divisible by 2. If 5, that means it is divisible by 5. Thus, their factors will be more than 2. So, you will not get any prime number. The answer is 0. 12. Observe that 3 is a prime number and 2 into 3 plus 1 is equal to 7 is also a prime. Are there other primes for which doubling and adding 1 gives another prime? Find at least 5 such examples. Examples could be like this. 5 into 2 plus 1 is equal to 11. 8 into 2 plus 1 is equal to 17. 9 into 2 plus 1 is equal to 19. 11 into 2 plus 1 is equal to 23. 15 into 2 plus 1 is equal to 31. Like that. 5.3 Co-prime numbers for safekeeping treasures. Which pairs are safe? Let us go back to the treasure finding game. This time, treasures are kept on two numbers. Jumpy gets the treasures only if he is able to reach both the numbers with the same jump size. There is also a new rule: a jump size of 1 is not allowed. Where should Grumpy place the treasures so that Jumpy cannot reach both the treasures? Will placing the treasures on 12 and 26 work? No. If the jump size is chosen to be 2, then Jumpy will reach both 12 and 26. What about 4 and 9? Jumpy cannot reach both using any jump size other than 1. So, Grumpy knows that the pair 4 and 9 is safe. Check if these pairs are safe. A. 15 and 39. Factors of 15: 1, 3, 5 and 15 itself. Factors of 39: 1, 3, 13 and 39 itself. You can see 3 is a common factor. So, if jump size is 3, Jumpy can reach both the numbers 15 and 39. B. 4 and 15. Factors of 4 is Factors of 15 is 1, 3, 5 and 15. You can see there is no common factor. So you can say the pair 4 and 15 is a safe pair. Similarly, see 18 and 29. You can do that. Since 29 is a prime number, so if you take at least one prime number, the pair will become safe pair. Similarly, D, 20 and 55. Since 5 is a common factor, this pair is not a safe pair. What is special about safe pairs? They don't have any common factor other than 1. Two numbers are said to be co-primes to each other if they have no common factor other than 1. Example, as 15 and 39 have 3 as a common factor, they are not coprime. But 4 and 9 are coprime. Which of the following pairs of numbers are coprime? A. 18 and 35. Factors of 18: 1, 2, 3, 6, 9 and 18. Factors of 35: 1, 5, 7 and 35. Since 18 and 35 has no common factor other than 1, they are coprime. B. 15 and 37. Factors of 15: 1, 3, 5 and 15. Factors of 37: 1 and 37. That means 15 and 37 are not coprime. That means 15 and 7 are coprimes as they have no common factor other than 1. See 30 and 415. You can see 30 has 0 at its unit place and 415 has 5 at its unit place. So both will have 5 as a common factor other than 1. So they are not coprime. Similarly, you can do D 17 and 69, E 81 and 18. While playing the Idli Vada game with different number pairs, Anshu observed something interesting. A. Sometimes the first common multiple was the same as the product of the other numbers. B. At other times, the first common multiple was less than the product of the two numbers. Find examples for each of the above. How is it related to the number pair being coprime? If the pair of numbers taken for Idli Vada game are coprimes, then their multiples will be the first number at which Idli Vada will be sold. Otherwise, if they have a common factor other than 1, a number that is less than their product will be the first one where Idli Vada will be sold. For example, let's take numbers 7 and 9. Multiples of 7 is 7, 14, 21, 28, 35 and so on. Multiples of 9 and so on. At these places, idli will be sold, and at these places, vada will be sold. And the multiples, that is common multiples of 7 and 9, that is 63, 126, 189, that is common multiple of 7 and 9. Idli vada will be said at the place of these numbers. You can see for the first time idli vada will be said at the place of 63, which is the product of 7 and 9. Let's take another example. A pair of numbers with having a common factor other than 1 such that they are not co-primes. For example, 6 and 9. Multiples of 6 and so on. Multiples of 9 and so on. At the place of common multiples, that is 18, 36 and so on, idli vada will be said. You can observe that 18 is the first number which is common multiple of 6 and 9, at which idli vada will be said, which is less than 6 into 9, that is 54, that is product of 6 and 9. This happens because they are not co-primes. In the first example, 7 and 9 are co-primes. In the second example, 6 and 9 are not co-primes. If we take numbers that are co-primes, the first time we will say idli vada is the number that is the product of those numbers, that is 7 and 9. But when we take non-co-prime numbers such as 6 and 9, we can say idli vada earlier than the number obtained after multiplying those numbers, that is 6 and 9. Co-prime art. Observe the following thread art. The first diagram has 12 pegs and the thread is tied to every fourth peg. We say that the thread gap is whole. The second diagram has 13 pegs and the thread gap is 3. What about the other diagrams? Observe these pictures, share and discuss your findings in class. In some diagrams, the thread is tied to every peg. In some, it is not. Is it related to the two numbers, the number of pegs and the thread gap being co-prime? In the first picture, you can see there are 12 pegs and the gap is 1, 2, 3 and 4. In the second picture, you can see there are 13 pegs and the gap is 4 minus 1, that is 3. In the third picture, you can see there are 16 pegs and thread gap is 8 minus 2, that is 6. In the last picture, you can see there are 24 pegs and thread gap is 12 minus 6, that is 6. You can see these numbers are non-co-primes, these numbers are non-co-primes, these numbers are non-co-primes. And you can observe that some pegs are left untied. In the second picture, you can see that 13 and 3 are co-primes, and you can observe that all pegs are tied to a thread. So there is no untied peg. This is because 13 and 3 are co-primes. Make such pictures for the following. A. 15 pegs, thread gap of 10. B. 10 pegs, thread gap of 7. C. 14 pegs, thread gap of 6. D. 8 pegs, thread gap of 3. 5.4 Prime factorization. Checking if two numbers are co-prime. Teacher, are 56 and 63 co-prime? Ansu and Guna, if they have a common factor other than 1, then they are not co-prime. Let us check. Ansu, I can write 56 14 into 4 and 63 21 into 3. So 14 and 4 are factors of 56. Further, 21 and 3 are factors of 63. So there are no common factors. The numbers are co-prime. Guna, hold on. I can also write 56 is equal to 7 into 8 and 63 is equal to 9 into 7. We see that 7 is a factor of both numbers. So they are not co-prime. Clearly, Guna is right as 7 is a common factor. But where did Ansu go wrong? Writing 56 is equal to 14 into 4 tells us that 14 and 4 are both factors of 56. But it does not tell all the factors of 56. The same holds for the factors of 63. Try another example, 80 and 63. There are many ways to factorize both numbers. 80 is equal to 14 into 2, 20 into 4, 10 into 8, 16 into 5, and so on. 63 is equal to 9 into 7, 3 into 21, and so on. We have written question marks to say that there may be more ways to factorize these numbers. But if we take any of the given factorization, for example, 80 is equal to 16 into 5 and 63 is equal to 9 into 7, then there are no common factors. Can we conclude that 80 and 63 are co-prime? As Ansu's mistake above shows, we cannot conclude that as there may be other ways to factorize the numbers. What this means is that we need a more systematic approach to check if two numbers are co-prime. Prime factorization. Take a number such as 56. It is composite as we saw that it can be written as 56 is equal to 4 into 14. So both 4 and 14 are factors of 56. Now take one of these, say 14. It is also composite and can be written as 14 is equal to 2 into 7. Therefore, 56 is equal to 4 into 2 into 7. Now, 4 is composite and can be written as 4 is equal to 2 into 2. Therefore, 56 is equal to 2 into 2 into 2 into 7. All the factors appearing here 2 and 7 are prime numbers, so we cannot divide them further. In conclusion, we have written 56 as a product of prime numbers. This is called a prime factorization of 56. The individual factors are called prime factors. For example, the prime factors of 56 are 2 and 7. Every number greater than 1 has a prime factorization. The idea is the same. Keep breaking the composite numbers into factors till only primes are left. The number 1 does not have any prime factorization. It is not divisible by any prime number. What is the prime factorization of a prime number like 7? It is 7. We cannot break it down any further. Let us see a few more examples. By going through different ways of breaking down the number, we wrote 63 as 3 into 3 into 7 and as 3 into 7 into 3. Are they different? Not really. The same prime numbers 3 and 7 occur in both cases. 3 appears 2 times in both and 7 appears once. Here you see 4 different ways to get prime factorization of 36. Observe that in all 4 cases we get 2 2's and 2 3's. Multiply back to see that you get 36 in all 4 cases. You can see 4 ways of breaking down 36 is given here. 18 into 2, 12 into 3, 9 into 4, 6 into 6. Again 18 has been broken down into 2 into 9, then 9 into 3 into 3. Similarly 12, 3 into 4, then 4, 2 into 2. Similarly here 4, 2 into 2, here 9, 3 into 3. Similarly 6, 2 into 3, 6, 2 into 3 here. You are getting 2 2's and 2 3's. 2 2's and 2 3's in all the 4 cases. For any number, it is a remarkable fact that there is only one prime factorization, except that prime factors may come in different orders. As we explained below, the order is not important. However, as we saw in these examples, there are many ways to arrive at the prime factorization. Does the order matter? Using this diagram, can you explain why 30 is equal to 2 into 3 into 5? No matter which way you multiply 2, 3 and 5. When multiplying numbers, we can do so in any order. The end result is the same. That is why when two 2's and two 3's are multiplied in any order, we get 36. In a later class, we shall study this under the names of commutativity and associativity of multiplication. Thus, the order does not matter. Usually, we write the prime numbers in increasing order. For example, 225 is equal to 3 into 3 into 5 into 5, or 30 is equal to 2 into 3 into 5. Prime factorization of a product of two numbers. When we find the prime factorization of a number, we first write it as a product of two factors. For example, 72 is equal to 12 into 6. Then we find the prime factorization of each of the factors. In the above example, 12 is equal to 2 into 2 into 3 and 6 is equal to 2 into 3. Now Can you say what the prime factorization of 72 is? The prime factorization of original number is obtained by putting these together. That is 72 is equal to 2 into 2 into 3 into 2 into 3. This is for 12 and this is for 6. We can also write this as 2 into 2 into 2 into 3 into 3. Multiply and check that you get 72 back. Observe how many times each prime factor occurs in the factorization of 72. Compare it with how many times it occurs in the factorization of 12 and 6 put together. Figure it out. 1. Find the prime factorizations of the following numbers: 64, 104, 105, 243, 320, 141, 728, 729, 1024, 1331, 1000. For example, I am doing for 728. You can do like this. So you can write 728 as 2 into 2 into 2 into 2 into 2 into 2, 6 times 2, 1, 2, 3, 4, 5, 6, and 3 times 3. Similarly, you can do for 1331. So the answer will be 11 into 11 into 11. 2. The prime factorization of a number has 1 2, 2 threes, and 1 11. What is the number? It is said 1 2, 2 threes, and 1 11. The number is 198. 3. Find 3 prime numbers, all less than 30, whose product is 1955. You can see 5 at its units place, so it will be divisible by 5. The answer is 5 into 17 into 23. So the three numbers are 5, 17 and 23. 4. Find the prime factorization of these numbers without multiplying first. A. 56 into 25. 56 can be split into 2 into 2 into 2 into 7. Similarly, 25 in 5 into 5. So the product 56 and 25 have the prime factors 2 into 2 into 2 into 5 into 5 into 7. That is all numbers present in the prime factorization of 56 and 25. Similarly, you can do B 108 into 75, C 1000 into 81. 5. What is the smallest number whose prime factorization has A. 3 different prime numbers, B. 4 different prime numbers? Try doing that. Prime factorization is of fundamental importance in the study of numbers. Let us discuss two ways in which it can be useful. Using prime factorization to check if two numbers are co-prime. Let us again take the numbers 56 and 63. How can we check if they are co-prime? We can use the prime factorization of both numbers. 56 is equal to 2 into 2 into 2 into 7 and 63 is equal to 3 into 3 into 7. Now we see that 7 is a prime factor of 56 as well as 63. Therefore, 56 and 63 are not co-prime. What about 80 and 63? Their prime factorization are as follows. 80 is equal to 2 into 2 into 2 into 2 into 5 and 63 is equal to 3 into 3 into 7. There are no common prime factors. Can we conclude that they are co-prime? Suppose they have a common factor that is composite. Would the prime factors of this composite common factor appear in the prime factorization of 80 and 63? Try doing that. Therefore, we can say that if there are no common prime factors, then the two numbers are co-prime. Let us see some examples. Example: consider 40 and 231. Their prime factorizations are as follows. 40 is equal to 2 into 2 into 2 into 5 and 231 is equal to 3 into 7 into 11. We see that there are no common primes that divide both 40 and 231. Indeed, the prime factors of 40 are 2 and 5, while the prime factors of 231 are 3, 7 and 11. Therefore, 40 and 231 are co-prime. Example: consider 242 and 195. Their prime factorizations are as follows. 242 is equal to 2 into 11 into 11 and 195 is equal to 3 into 3 into 13. The prime factorization of 242 are 2 and 11. The prime factorization of 195 are 3, 5 and 13. There are no common prime factors. Therefore, 242 and 195 are co-prime. Using prime factorization to check if one number is divisible by another. We can say that if one number is divisible by another, the prime factorization of the second number is included in the prime factorization of the first number. We say that 48 is divisible by 12 because when we divide 48 by 12, the remainder is 0. How can we check if one number is divisible by another without carrying out long division? Example: is 168 divisible by 12? Find the prime factorizations of both. 168 is equal to 2 into 2 into 2 into 3 into 7 and 12 is equal to 2 into 2 into 3. Since we can multiply in any order, now it is clear that 168 is equal to 2 into 2 into 3 into 2 into 7, that is 12 into 14. Therefore, 168 is divisible by 12. Example: is 75 divisible by 21? Find the prime factorizations of both. 75 is equal to 3 into 5 into 5 and 21 is equal to 3 into 7. As we saw in the discussion above, if 75 was a multiple of 21, then all prime factors of 21 would also be prime factors of 75. However, 7 is a prime factor of 21 but not a prime factor of 75. Therefore, 75 is not divisible by 21. Example: is 42 divisible by 12? Find the prime factorization of both. 42 is equal to 2 into 3 into 7 and 12 is equal to 2 into 2 into 3. All prime factors of 12 are also prime factors of 42. But the prime factorization of 12 is not included in the prime factorization of 42. This is because 2 occurs twice in the prime factorization of 12 but only once in the prime factorization of 42. This means that 42 is not divisible by 12. We can say that if one number is divisible by another, then the prime factorization of the second number is included in the prime factorization of the first number. Figure it out. 1. Are the following pairs of numbers co-prime? Guess first and then use prime factorization to verify your answer. A 30 and 45. Let's find their prime factorization. 30 is equal to 2 into 15 or 2 into 3 into 5. Similarly, 45 is equal to 3 into 15 or 3 into 3 into 5. You can see 3 as a common factor as well as 5. So they are not co-primes. Since all the factors of 1 is not included in the factors of other, so they are not completely divisible. B. 57 and 85. 57 can be written as 3 into 19. 85 can be written as 5 into 17. Since they don't have any common factor other than 1, so they are co-primes. Similarly, you can do C 121 and 1331, D 343 and 216. 2 is the first number divisible by the second. Use prime factorization. A 225 and 27. Prime factorization of 225 is 3 into 5 into 3 into 5. Similarly, for 27, you can write 3 into 3 into 3. Since this is not included here, so first number is not completely divisible by the second number. B. 96 and 24. 96 is equal to 4 into 24 or 2 into 2 into 2 into 2 into 2 into 3. Similarly, 24 can be written as 2 into 2 into 2 into 3. You can see 2 into 2 into 2 into 3 is included here. So you can say 96 is completely divisible by 24. Similarly, you can find C 343 and 17, D 999 and 99. 3. The first number has prime factorization 2 into 3 into 7 and the second number has a prime factorization 3 into 7 into 11. Are they co-prime? Does one of them divide the other? Since they have 3 as a factor other than 1, they are not co-prime. And since all the factors of one number is not included in the factors of other number, so we can say one of them will not divide the other completely. 4. Guna says any two prime numbers are co-prime. Is he right? Yes. We already know prime numbers has exactly two factors, that is 1 and the number itself. So if you take two prime numbers, then their factors will never match. 5.5 Divisibility tests. So far, we have been finding factors of numbers in different contexts, including to determine if a number is prime or not, or if a given pair of numbers is co-prime or not. It is easy to find factors of small numbers. How do we find factors of a large number? Let us take 8560. Does it have any factors from 2 to 10? 2, 3, 4, 5 like that, 9 and 10. It is easy to check if some of these numbers are factors or not without doing long division. Can you find them? Divisibility by 10. Let us take 10. Is 8560 divisible by 10? This is another way of asking if 10 is a factor of 8560. For this, we can look at the pattern in the multiples of 10. The first few multiples of 10 are 10, 20, 30, 40, like that. Continue this sequence and observe the pattern. You will repeat that, you will get numbers like 1000, 5000, 8000, then 8010, 8020, like that, 8500, then 8560. Is 125 a multiple of 10? Will this number appear in the previous sequence? Why or why not? You can observe that any number that is multiple of 10 has at least 0 at its units place. Can you now answer if 8560 is divisible by 10? Consider this statement. Numbers that are divisible by 10 are those that end with 0. Do you agree? Divisibility by 5. The number 5 is another number whose divisibility can easily be checked. How do we do it? Explore by listing down the multiples 5, 10, 15, 20, 25, and so on. What do you observe about these numbers? Do you see a pattern in the last digit? What is the largest number less than 399 that is divisible by 5? Is 8560 divisible by 5? If you repeat this pattern, you will see any number ending with 0 or 5 is divisible by 5. So, you can say 8560 is divisible by 5. A number less than 399 that is divisible by 5 is 395. Consider this statement. Numbers that are divisible by 5 are those that end with either a0 or a5. Do you agree? Divisibility by 2. The first few multiples of 2 are 2, 4, 6, 8, 10, 12, 14, 16, 18, 24, and so on. What do you observe? Do you see a pattern in the last digit? Yes, you can see digits 2, 4, 6, 8, 0, 2, 4, 6, 8, 0, and so on. They will repeat. Is 682 divisible by 2? Yes, it ends with 2, so it will be divisible by 2. Can we answer this without doing the long division? Yes, we can. Is 8560 divisible by 2? Why or why not? Yes, it is divisible as it ends with 0. Consider this statement. Numbers that are divisible by 2 are those that end with 0, 2, 4, 6, or 8. Do you agree? What are all the multiples of 2 between 399 and 411? The answer is 400, 402, 404, 406, 408, 410. Divisibility by 4. Checking if a number is divisible by 4 can also be done easily. Look at its multiples 4, 8, 12, 16, 20, 24, 28, 32, and so on. Are you able to observe any patterns that can be used? The multiples of 10, 5, and 2 have a pattern in their last digits which we are able to use to check for divisibility. Similarly, can we check if the number is divisible by 4 by looking at the last digit? It does not work. Look at 12 and 22. They have the same last digit, but 12 is a multiple of 4 while 22 is not. Similarly, 14 and 24 have the same last digit, but 14 is not a multiple of 4 while 24 is. Similarly, 16 and 26 or 18 and 28. What this means is that by looking at the last digit, we cannot tell whether a number is a multiple of 4. Can we answer the question by looking at more digits? Make a list of multiples of 4 between 1 and 200 and search for a pattern. Find numbers between 330 and 340 that are divisible by 4. Also find numbers between 1730 and 1740 and 2030 and 2040 that are divisible by 4. What do you observe? Is 8536 divisible by 4? Consider these statements. A. Only the last two digits matter when deciding if a given number is divisible by 4. B. If the number formed by the last two digits is divisible by 4, then the original number is divisible by 4. C. If the original number is divisible by 4, then the number formed by the last two digits is divisible by 4. Do you agree? Why or why not? Divisibility by 8. Interestingly, even checking for divisibility by 8 can be simplified. Can the last two digits be used for this? Find numbers between 120 and 140 that are divisible by 8. Also find numbers between 1120 and 1140 and 3120 and 3140 that are divisible by 8. What do you observe? Change the last two digits of 8560 so that the resulting number is a multiple of 8. Consider this statement. A. Only the last three digits matter when deciding if a given number is divisible by 8. B. If the number formed by the last three digits is divisible by 8, then the original number is divisible by 8. C. If the original number is divisible by 8, then the number formed by the last three digits is divisible by 8. Do you agree? Why or why not? We have seen that long division is not always needed to check if a number is a factor or not. We have made use of certain observations to come up with simple methods for 10, 5, 2, 4, 8. Do we have such simple methods for other numbers as well? We will discuss simple methods to test divisibility by 3, 6, 7 and 9 in later classes. Figure it out. 1. 2024 is a leap year as February has 29 days. Leap years occur in the years that are multiples of 4, except for those years that are evenly divisible by 100 but not 400. A. From the year you were born till now, which years were leap years? B. From the year 2024 till 2099, how many leap years are there? 2. Find the largest and smallest 4-digit numbers that are divisible by 4 and are also palindromes. 3. Explore and find out if each statement is always true, sometimes true, or never true. You can give examples to support your reasoning. A. Sum of two even numbers gives a multiple of 4. B. Sum of two odd numbers give a multiple of 4. Or find the remainders obtained when each of the following numbers are divided by 10, 5 and 2. 78, 99, 173, 572, 980, 1111, 2345. 5. The teacher asked if 14,560 is divisible by all of 2, 4, 5, 8 and 10. Guna checked for divisibility of 14,560 by only two of these numbers and then declared that it was also divisible by all of them. What could those two numbers be? 6. Which of the following numbers are divisible by all of 2, 4, 5, 8 and 10? 572, 2352, 5,600, 6,000, 7 crore 76 lakh 22,160. 7. Write two numbers whose product is 10,000. The two numbers should not have 0 as the units digit. 5.6. Fun with numbers. Special numbers. There are 4 numbers in this box. Which number looks special to you? Why do you say so? You can see this is 1 digit, this is 2 digit, 2 digit, 2 digit. Other way of seeing this, you can see these numbers are perfect squares, but 43 is not. Look at the what Guna's classmates have to share. Karnavati says 9 is special because it is a single digit number, whereas all the other numbers are 2-digit numbers. Gurupreet says 9 is special because it is the only number that is a multiple of 3. Murugan says 16 is special because it is the only even number and also the only multiple of 4. Gopika says 25 is special as it is the only multiple of 5. Yagyaki says 43 is special because it is the only prime number. Radha says 43 is special because it is the only number that is not a square. Below are some boxes with 4 numbers in each box. Within each box, try to say how each number is special compared to the rest. Share with your classmates and find out who else gave the same reasons as you did. Did anyone give different reasons that may not have occurred to you? A prime puzzle. The figure on the left shows the puzzle. The figure on the right shows the solution of the puzzle. Think what the rules can be to solve the puzzle. You can see 170 here, that is 5 into 2 into 17, that is 5 into 2 10 and 10 into 17 170. Similarly 5 into 3 15, 15 into 2 30. Similarly 3 into 7 21, 21 into 3 63. That is in the column. If you see the rows, you will observe the same pattern. 5 into 5 25, 25 into 3 75. 2 into 3, 6. 6 into 7, 42. Similarly, 17 into 2, 34. 34 into 3, 102. Rules. Fill the grid with prime numbers only so that the product of each row is the number to the right of the row and the product of each column is the number below the column. Summary. If a number is divisible by another, the second number is called a factor of the first. For example, 4 is a factor of 12 because 12 is divisible by 4. 12 divided by 4 is equal to 3. Prime numbers are numbers like 2, 3, 5, 7, 11, and so on that have only two factors, namely 1 and themselves. Composite numbers are numbers like 4, 6, 8, 9, and so on that have more than two factors, that is, at least one factor other than 1 and themselves. For example, 8 has the factor 4 and 9 has the factor 3, so 8 and 9 are both composite. Every number greater than 1 can be written as a product of prime numbers. This is called the number's prime factorization. For example, 84 is equal to 2 into 2 into 3 into 7. There is only one way to factorize a number into primes, except for the ordering of the factors. Two numbers that do not have a common factor other than 1 are said to be coprime. To check if two numbers are coprime, we can first find their prime factorizations and check if there is a common prime factor. If there is no common prime factor, they are coprime, and otherwise they are not. A number is a factor of another number if the prime factorization of the first number is included in the prime factorization of the second number. For more videos, you can subscribe NCERT video. Thank you.